Good morning. This is already third day. Hope you learned a few things. And today we are going to talk about traffic signal design. I'm not sure how many of you know this topic in depth. I'm going to assume you do not have much of knowledge. So we'll have a morning 2 hours talking about this. And then in the afternoon, we'll try to do optimization of a timing plan using Excel and using genetic algorithm. And then we'll talk about multimodal component of transit signal priority. That's going to be today's lectures and tutorial. So the basics of signal timing plan. Obviously, we want to know why we put the signals. The cost of a traffic signal is not trivial, at least in the US. If you want to install fully loaded traffic light controllers and posts and everything, it's about 150, almost 200,000 US dollars. So it's not cheap, but it does have a huge mobility benefit. As you have more cars approaching at the intersection, two-way stops or four-way stops are not going to work when it exceeds a certain volume level. So signal actually gives right-of-ways to make it much safer as well and better efficiency. Costs and maintenance. And then also as the demand changes in the network and then volume slightly increases, timing plan could be outdated and they need to be updated. But a lot of agencies, they do not have budget or efforts to, time and efforts to update them as frequent as needed. So that's one downside. And obviously a lot of the cost associated with it. This is a report given by the timing having to be up to date. So if you keep the good timing plan, you can actually reduce delay up to 40%, travel time up to 25%, stops are reduced up to 40%. Somebody actually converted this into how much benefit we could give to drivers, public. So assume each person is spending about 2 hours per day for commuting and also going to the grocery or go to restaurant and activities. And if we add up these percentage, and it could be about 50 hours per year. That means you have extra 1 week of vacation. So kind of sales pitch to make sure that timings are updated. In case you ever wanted to talk about who actually started this traffic signal very first time, this is 1868 in London. As you can see here, it's not traffic light. It's basically go and stop indicator, and then person is actually turning around and giving the guidance. This was needed because if you do not have a priority given to other approach vehicles, and there's a lot of weavings and congestions. So this was one idea they started it. And in the US, they had a first electric traffic signal in Cleveland, Ohio. Not sure why that was the first place. And then Salt Lake and others. That's a 1914. So it's been almost a century or longer. And believe it or not, they had an actuated signal in Baltimore, Maryland in 1928. Actuated meaning that they change the duration of green time based on the demand. So it's a good. So the control of the intersections, you don't have to have an intersection as a traffic signalized one. You can have a stop controlled, yield controlled, or traffic light controlled, and you have roundabouts and other things as well. One question you might have is that how do we decide which one's most appropriate? And who actually decides that? If you actually have money and ways of putting traffic signals, it's not going to be the best option when you have a low traffic volume. One evidence is that maybe it's not in India. In the US, some of the intersections are going into flash yellow, flashy red mode at night. Those flashy red is a stop sign. Flash yellow, you sort of yield, and then you have right away. It's making two-way stop control intersection. So it's basically telling that with the low volume, signals are not the best option. So the volumes are one indicator to decide whether we should do signal or not. But again, who's going to decide this? It's going to be the politicians affecting, I need a traffic light in my neighborhood, or a city mayor has a say to need one, or citizens complaining about we need to have a signal, traffic engineers deciding what to do. What's the most important one is basically using the something called the MUTCD. It's a documentation trying to maintain uniform control devices, and they have a device information about how to determine traffic control device at the intersections. It's called the warrants. The warrants was developed and it has evolved over time as well. So we rely on this. And some of the policy questions are traffic calming versus efficiency. If you have actually really bad coordination between the intersections, some people think that that's achieving traffic calming. So everybody stops every intersection. Or efficiency-wise, you want to have a good progressions. How do you have the policies on those? And also needing to have an engineering study. This is again the issue of lawsuits and liabilities. When the warrants on this MUTCD is not about we shall have a traffic light if the conditions are met. It's not. It's basically triggering, we call it engineering study to figure out do we really want to install traffic light? And this usually goes with priorities. So you have maybe X number of intersections that actually met with the warrants. And you don't have money for 10, usually you don't. And you have to make a priorities. And then where you have engineers are coming in and look at the conditions. They also consider safety concerns, the number of crashes, not just delays and volumes. So engineering study is a very important component. They also use HCM for understanding the level of service, often do the simulation analysis as well. So the management of traffic signals are based on the, do we need a new signals? And then when we need a signal, how do we design them? How do we put the settings? And we want to have a field evaluation, whether this is working as we expected. Oftentimes, we rely on a simulation tool to sort of estimate what's going to happen of new signal, new timing plan. And especially when you have the coordinated system, they don't work exactly they want to. And often engineers go out in the field and observe conditions and change the offsets a few seconds or change the amount of durations a few seconds as well, so they can improve signals. And also, people can consider removal of signals. Some are in favor of roundabouts. So taking out the signal and putting the roundabout. And most studies show that roundabout is safer in terms of crash severities. And think about the intersections. If you have red-light runners, the crash has a high severity versus the roundabout. It's usually a rear-end crash, usually not that severe ones. And also, it often provides a much higher capacity than intersections. The challenge, at least in the US, at the early stage was people don't know how to drive at the roundabout. Should I yield to go in, or should I wait until I find the gap, kind of thing. And then they actually do well now, and then US is adopting more roundabouts as well. Some of the decisions, obviously the warrants study is helping you decide a new signal is needed. And then design and settings, we can do the signal design and optimizations. Some of the design elements could be lane assignment. Do we want to have left and through going together versus separate left turns? It's also an interesting design element. And obviously optimizing it, how long the cycle should be, and duration of green times are important. Field evaluation, all these are basically common sense of knowledge. We can look at the queue length. There's one easy way to evaluate conditions. Looking at it as a corridors and do the sort of pro-vehicle trial runs. So you just drive through the area. And nowadays, the people actually use a GPS. They can tell at the end of the run which signal is getting the progression, where you stop them, can you make some improvements, and things like that can be actually easily done. So going into the signal control parameters, you probably know these: cycle length, green time and clearance interval, phase sequence, and offsets for coordinated systems. How many of you do not know this? Oh, this is really basic, so we could easily go skip. Okay, so phase is very easy. Indication of the concurrent green indications. So whatever, this is a simple two phases. When you have two phases, usually main street greens are on, and then second phase, cross street greens are on. Fairly easy. Left-turn treatment is kind of interesting. I don't know how much you understand this. Treatment of left turn is important. Used to be driver's expectancy is that left turns coming first and then throughs. And when you do have this operation only, and certain spacing of the intersections, it's very difficult to provide a progression because you have a duration of left turns, and then that's blocking how you actually operate the offsets. So by switching this left turn to maybe through and then left, you can actually provide a better progressions. And concern was that people do expect that left comes first and then through. There was some concerns about safety. So in the US, if they do change, they show that green comes first at this intersection or something like that. This is also useful for both bidirectional progressions. So one case, you need the left first to make a progression. The other direction, you might need a through first to make a better progression. So that's one way to treat them. And this can be optimized as well. I mean, you cannot do manually all these for 5, 10 intersections. And optimization can take care of this. That works as well.
Just to clarify, in our situation, it will be right turn. Because we are driving on the other side.
Thank you very much. Thank you. Right turns. Thank you. So it's still the right of way, not left of way though. Cycle length, you know the duration of the sequence of the phases and then green times all together. This also plays a role in terms of peak, off-peak, and non-peak hours. Usually we need to have a longer cycle for peak hours, more cars need the green times, and then when you go into midday and off-peak, you might need shorter cycles. The challenge obviously is that changing between these two cycle lengths. If it's not coordinated, no problem. But if you have multiple intersections being coordinated, then transition between the one cycle to another is not a trivial. And this is going to be a problem for emergency vehicle preemptions. I don't know how much is in India. When the fire trucks and ambulances, they can actually request for green at the intersection. And usually in the US, once you complete the so-called minimum green time, you open up green time for whoever is requesting these preemptions. And this is actually helping saving lives, and it's very good, but this is disrupting the progression as well. So that's some challenge that needs to be addressed well. Again, green times are easy. Yellow and then all red. Not sure, do you understand the all red time? and which is not easy to observe, obviously. So when you have an end of green and we provide yellow, and then sometimes yellow is not long enough, this is for safety, obviously. If the car is trying to get through the intersection when they saw yellow and then they don't stop and they are continuously traveling, and oftentimes they are still in the intersection at the end of yellow. And typically we add about a second of all red. It means that every phase of the signal is seeing red time that clear up those vehicles. Obvious downside is that people do know that, they still try to get in, and it's not good, but we need to have that for safety reasons. This is a typical way of doing phase. This is without having pedestrians, so it's fairly easy to give phase 1 and phase 2 and phase 3. So these sort of not dark black one is permissive. So they do not get left turn arrow or right turn arrow. They can just make their own way of making turns. It's fairly common as well, especially you have a single lane per direction case. And this is when you have pedestrians or bicyclists. They actually have greens are being. I have not started this. Is this the one? Oops. Sorry. This is the one?
Yeah, I think
No, not that one.
no.
This one?
No, it's on the top now.
It's good.
Yeah.
It magically appeared. So we went back to it. Okay, thank you. So during the green time, we have a portion of the green is, obviously this is for when you have intersections, and this guy is showing the green here, then they will have a crossing, right? So the green duration is divided into walk and flash don't walk. So it's a fairly long flash don't walk, and now a lot of intersections are showing the countdown. They show the remaining of pedestrian walk time, so that's good. And then a fairly long don't walk as well. So this will allow to have pedestrians and bicyclists to cross. Again, one of the challenges is that there's a pedestrian crossing time is needed. So typical pedestrian requires about 3 feet per second walking speed, and depends on how many pedestrians are waiting, and you can estimate how long does it take to cross, especially you have a multi-lane, 6-lane road, wide road, and often this is amazing. I'm gonna just try one more time. I'm gonna just exaggerate this. So this is a street. So this is a major street, right? When you are getting green time for cross street, compared to major road, your duration of green time is probably very small. It's not 50-50, it's probably 20-80. So your cycle length is even 150 seconds, and your green time is less than 20 seconds or 15 seconds. And during 15 seconds, they cannot cross entire street. It's a big challenge. It depends on how many pedestrians or bicyclists you have to serve. If you have a heavy pedestrian volume road, you have to make sure that green times are long enough, even though cars are not utilizing it. Or if it's a low pedestrian volume in the US, they just have a pedestrian actuation button that you person pushes it, and then only that cycle is providing long enough green for safely crossing entire road. So that's something to keep in mind. And showing the same thing with the controllers and different phases. Different textbook or different controller uses slightly different names for the terminologies, but you probably can figure it out. cycle lengths and phase, or similar to the durations of the phases or intervals, yellow and red clearance time. Offsets are key to making progression along the major corridor. So by definition, it is showing time difference between the beginning of green time at the one intersection or master intersection to the beginning of green time at the other intersection. So when cars are started moving at the beginning of green, and then they travel to the downstream intersection, we want to make sure that they can see the green time. One challenge is if there's a remaining vehicle as a queued vehicles, and when they arrive on time, assuming no queued vehicles, it's creating problems. So we'll have to add a queue clearance time into the offset calculations. That's another challenge. And then you have to do the both bidirections. Sometimes that's not easy. So that's the real basic of the signal timing plans. I want to explain the highway capacity manual, how they do in terms of signal control. Have you learned this from the Indo HCM? Some, not everyone. Okay. It's probably similar concept. So they start with the level of service concept. It's affecting based on the number of vehicles, obviously, and also distribution of the vehicle. Lane utilization is one thing, and also heavy vehicles are another thing, and also geometric conditions. More the lanes, you can push more vehicles out. And one thing we are focusing on is obviously signal system in terms of cycle and green times and those settings. So these are settings, once you have a signal, it's fairly easy to update. So it's a very cost-effective way of improving mobility and also safety as well. MOEs is called control delay. I think I mentioned a little bit. Control delay is, so they evolved from stop delay to approach delay, and now they call this control delay. Stop delay only considered complete stop times. So when you actually come into the intersection and you stop because the traffic light is red, and how long you stop them is the key elements. And then they begin to realize that vehicles are also delayed while slowing down to stop, and then stop to the accelerating to gain whatever their speed. So this is a so-called approach delay. And then they also realize that cars are interacting each other. If you are on the leftmost lane and try to make a right turn, and then that's going to have interactions with other cars. And that's creating delays. Or do a lot of lane changes causing effect. So they include everything as a control delay. And because of this, used to be level of service F was 60 seconds per vehicle. Now they made it as 80 seconds per vehicle. Again, this is a consensus. This is probably a very high level of how signalized intersection is analyzed. They are focusing on demand side and supply side. So if you are taking Economics 101, demand and supply is the basic concept for determining microeconomics. And here, demand is given by how many cars are coming in. And instead of counting just number of cars they arrive, HCM wanted to look at the peak of 15 minutes. And don't ask me why 15 minutes. It could have been a minute, but they decided to have a 15 minute as a good interval for collecting cars back in probably 60s and 80s. And using that information, and they are trying to look at the worst 15 minutes. And they want to deal with worst 15 minutes happening for entire hour. In part of the reason is that if you have a 4 different approach, having 8 different turns, like a throughs and right turns, and each has a different 15-minute pickings. And the worst case is that worst 15 minutes happening at the same time. We probably want to deal with it instead of average conditions all the time. So that's looking at sort of conditions for this peak hour factor we kind of mentioned. And then this should be a left turn on red, I guess. So cars go away even though they don't get the green. they can just make left turns. And also defining lane groups is another concept which is fairly straightforward. And then supply side is that what the HCM is doing is, let's assume it's ideal condition and all 100% green and infinite number of queued vehicles. How many cars can get through this approach, this lane? And then they apply conditions. Let's say this is a lot of heavy vehicles. There's a lot of bus bays. There's a parking maneuvers. They try to reduce the saturation flow rate. So this is one way to calculate saturation flow rate as a theoretical way. Or you could go outside and then collect number of cars passing at the stop bar, how many cars are passing through, and you can probably look at the headway, and then what is the saturation headway? Under saturation, how many cars can get through? So once you know saturation headway, flow rate or saturation flow rate is 3600 over saturation headway, so you can actually calculate them. So that is something you can actually calculate for supply side. And supply side is not 100% given green to each approach. So they share the green time based on cycle length. So you have cycle length and you can actually calculate so-called capacity. If you have saturation flow rate times, maybe you have duration of green time over cycle length, giving you what's your capacity to provide. So that's the so-called V over C ratio. In the HCM, V over C ratio is a key variable to determine delay, control delay. And based on this, you can get all different performance measures. So this is how you understand performance of your signalized intersections. And obviously, you can improve this operation by changing cycle length, and you look at the delay. Changing duration of green times, you look at the delay, so you can actually sort of optimize your signal settings as well. So the HCM gives how to evaluate performance of the intersection with the different geometry, different volume, and then change of the signal settings. Obviously, capacity analysis is the key. We change number of phases. You could have 2 throughs only, or you could have 8 phases and so forth, and cycle length and duration of green times are design elements. I'm not going to read all these lines, but the key is input of the HCM is the geometry conditions, the number of lanes. And we also consider the area type, because the CBD area, Central Business District, has more activities and they have less throughput because of a lot of parking maneuvers and even the delivery vehicles and so forth. Lane width, grades, turning movements, exclusive turning movement lanes is important. Parking is another factors, and traffic conditions, number of cars are important. So-called the base saturation flow is ideal situations, so S naught, and you multiply all those adjustment factors to make a realistic saturation flow rate, and then we decide the cycle length. There's some concerns about minimum green time. Again, this is driver's expectancy. You don't want to have a green time showing only 2 seconds or 3 seconds. Once you start the green, usually minimum green is 5 seconds for turning movement, and throughs are usually given as at least 7 to 9 or 10 seconds. And also you have a sensors, then you can actually decide the green time as well. So you have a sensor somewhere upstream, and then beginning of red, you can count how many cars are coming in, and that should decide the initial green time. At least you want to clear up those vehicles queued during red time. And also minimum pedestrian green time based on the pedestrian speed, walking speed, and also number of pedestrians. So they even consider there's a X number of 10 or 100 pedestrians, and they assume this is a sidewalk and this is the 2 ways, and they're going to be align each other to go one way, and there's 4 people per row, and then this is 6 rows are needed. So you can actually add that up to clear the pedestrian crossing. In real world, they are just mixed through, so it's not always work like that. But there's a way of considering those initial conditions. We talked about this concept of peak hour factors. The idea is that when we decide the peak hour, it's not like 7 to 8, 8 to 9. We are looking at a rolling 1 hour window. So this is one example. Let me go back. This is one example of showing that. So you have a 7 to 8:15 or longer, and we are not simply looking at the 7 to 8 and then 8 to 9. We are doing rolling of these, and in this case, 7:15 to 8:15 has a higher volume. So that's our peak hour. So the peak hour doesn't have to be whole hour durations, and this is a peak hour factor equation. So basically, what we are doing is total hourly volume during the peak hour divided by maximum 15 minutes existing for entire hour. So 4 times a peak of 15 minutes. So this is assuming 2400, and the maximum vehicle volume is 650. So, okay. So this is my peak hour, and out of these 4, this is the highest peak hour volume. So your peak hour factor is basically 2400 divided by 650 times 4. I have that actually equation next page. So this is how you calculate them. So 0.923 is the peak hour factor. What it means is that once we know the area of peak hour factor, and I just need to have a peak hour volume, and I inflate the volume to be, instead of 2400, here I'm going to inflate that volume to be 2600. So this is assuming that worst of 15 minutes is happening for the entire hour. That's how the HCM is doing it. Flow rate is also a similar way. You can do a 15 minute, 60 minute as a single period or multiple period. But if you consider peak hour factor, you're basically considering worst of 15 minutes happening for the entire hour. Saturation flow rate I mentioned about. You can use field observation or estimating using the HCM equation. Again, by definition, it's assuming 100% green for entire duration, passenger PCE, passenger car unit, only passenger cars. They just keep moving, and how many cars are getting through. So typically in the US, it could be 1800, sometimes 1750 or 1850, depends on the situations. So these are the adjustment factors. So I mentioned about S0 as ideal saturation, base saturation flow. So I could assume this as 1800. And in reality, you may not be able to see 1800 because of lane width is narrow. Maybe there's heavy vehicles, there's grades on the slope side, and bus bays, and an area which is not CBDs, and lane utilization is poor. This could happen, as I mentioned. There's a bus syndrome. There's a bus. Nobody will try to follow. Not many people follow that bus. So you have unbalanced lane utilization that will affect on your saturation flow rate. All these are the factors, and it's available in the HCM. I'm sure it's the same thing as in your Indo HCM as well. Sometimes the people use the 1900 as well. Adjustment for these and others are commonly done. Parkings are affecting as well. Bus blockage is another challenging issue. Bus often blocks vehicles. So that's why, the Professor Goswami actually mentioned about a near side bus or a far side bus stop. So people favor to have a far side bus stop because of that issue. If you have a near side bus, and then even though you see the green and the bus is stopping and you cannot actually move, the simple calculation of doing how you actually estimate saturation flow rate. Again, this is probably fairly straightforward. So we assume 1900 as a saturation flow rate per lane. So you have to multiply number of lanes as n, and then lane width is not 12 foot, then you modify based on this. So this is the baseline saturation flow rate. Sometimes people forget to multiply by number of lanes. That's important. And lane width adjustment, 12 foot. 12 feet is the ideal case. It's less than that, and you use this equation to adjust. So narrower the lane, your saturation flow rate is lower, obviously. And then heavy vehicle percentage is also adjusted. And then in your case, you have a CBD. Again, CBD has a lot of activities, and they may not be able to utilize the entire base saturation flow rate. Some of the terminologies, startup loss time is probably you know this, saturation flow rate you know. Effective green time, I'm going to explain that, and VOC ratio is another terminologies. So this is in a way to look at how signal can be operated. So this is a time domain here, as a time domain here, and this is a saturation flow rate. So during red, no one utilizes time, no one, except for maybe emergency vehicles. So typical cars are not using it. And at the beginning of green, it's impossible to start at the same time as green starts. There's a countdown signals in the China. I don't know, Indo has it or not. You have it? Okay. So it might help a little bit reducing start of loss time. So they actually lose a certain seconds, and then they pick up, and then they operate as saturation flow rate. And then once you actually clear up the queue, then you don't have saturation flow out, right? So this is actually arrival patterns. And then at the beginning of yellow, most people do not stop. Yellow means you have a chance to get through, right? So they utilize a portion of yellow as if it's a green. So if you are talking about effective green time, so the big green bar is display the green time. And in reality, people are using effective green time. So lose something at the beginning, and then they gain some at the end of green, so utilizing some of the yellow time. So this is what's happening in signal control. So how do we estimate startup loss time? Maybe this is not ideal for India case. This is a time between the vehicles, those are queued. So the key is that when you calculate this saturation flow rate from the field, you actually have a queued vehicles. You don't consider vehicles joining at the end of a queue. It has to be queued vehicle at the beginning of green. You could add one or two more if they're not moving, but to be safe, you want to consider queued vehicles at the stop bar. And then maybe this is the time taken from the first vehicle at the beginning of the green, and this might take a 2 point something, maybe 2.4 seconds. And second vehicle maybe slightly less, third might be less. And if you go fourth or fifth vehicles, they might be stabilizing. This could be 2 seconds or 1.9 seconds, depending on how fast you are moving. So this is the headway that we are looking for as saturation headway. And before that time, these bars are sort of startup loss time. It's not just the first vehicle, it's happening at least a few vehicles at the beginning. And this is a loss time when we actually saw here the first this time portion of this is a loss time, right? So that's a loss time that we are calculating. We can estimate from the field, and you want to do this for a few trials, not just single time. And then that way you can actually get the startup loss time from the field, and also calculate, this is weird position, but if you want to know the H as 1.9 or 2 seconds, you can actually calculate saturation flow rate from the field. So this is how you estimate saturation flow rate from field conditions. This is an example. If you want to try it, that's fairly straightforward. So if you found that average headway after startup loss time is 2.2, and you get about 1636 as a saturation flow rate per lane. Per lane is important. This is another example that you can try out. So this is the queue positions This is the trial number 1. So I have a cycle number 1 to 10. So I'm doing this 10 times at 10 different cycles. And then first the cycle has a 7 vehicles queued. Oops. And second cycle is a 10 vehicle queued, and a slightly different number of vehicles queued, obviously. And if you look at these, maybe 1.9 might be the saturation headway, but this is not the case here. This is not the case here. So there's some unbalanced, not always true, right? Then how do you deal with it? One suggestion is that you can probably take an average. So here you can take average by 10, here average take by 4. So you can actually see this. Oh, okay, looks like a 2.0 might be the one. So it happens as 1.9 once in a while, more than 2 something, 2.1s are happening as well. So we want to try maybe this range of the value as a saturation headway. Again, this is not rocket science. This is commonly used. So that's how you calculate a saturation flow rate for the HCM method. Effective green time is the same thing we mentioned. So in transportation, we use lower character, upper character differently. Big G is phase time or displayed green time, and then small g with the E is effective green time. So we sum them up from the this displayed green time and yellow and red clearance time, and then we subtract lost times. Then that's going to be effective green time. This is similar to what we saw on that big chart, looking at the relationship between start of lost time, and then we lose something at the beginning of green, and then we gain something during the yellow. That's what this is. That's exactly what I was talking about. Same idea of. Again, this is obvious. Interesting. And then we don't use the entire yellow, because the people are beginning to worry there's a yellow been on some seconds, and I don't want to make, I don't want to put myself into danger. Maybe that's my philosophy, and some people may different philosophy of I don't want to get a fine or something. Next concept is the capacity. So supply side of a signal is not 100% given to one approach. It has to be shared by different approach or phases. So whatever the capacity, capacity that we want to get is based on saturation flow rate. That's if we have 100% green, this is what we can process. And this is shared by portion of a green by the cycle length. So you have a cycle length of 100 seconds. I can utilize my approach, my effective green time duration. So that's why we get this equation. It's fairly straightforward as well. And this kind of shows that, so I know the V and I know the small c capacity. So again, lower and upper characters are different. The small c is a capacity, big C is a cycle length. So the reason I'm showing this is, so if you actually, capacity as saturation times G over C, and then if you rearrange this, this is what you get. Here, V over S is something that is a fixed. Once you have a signalized intersection as a geometry and then volume, and V over S is a fixed, right? C over G is something we can control. We can have a longer or smaller cycles. That's creating different V over C ratios, right? Right. This is fixed. So the key, and then also V is also fixed, right? So the capacity is a function of different cycles and different green times. So obvious. And how do we play with this to control V over C ratio? If you think about economics 101, you don't want to have conditions for every time you have a situation that's a one-to-one match. You want to have some rooms available to consider emergency case. So you want to have some redundancies. So your V, we don't want to have a V is equal to C all the time. If that's the case, it works for average conditions. It's not going to work whatever the over fluctuating condition. It's okay for under fluctuating conditions. So typically we decide what V over C ratio we want to design for. And again, this depends on the volumes. If it's a low volume, you don't want to have a very big V over C ratio. But if you have a fairly big V volume, you don't want to have very small V over C ratios. So typically people use 0.85 as if it's a reasonable volume, and try to do 0.9 or sometimes 0.95. If it's a very oversaturated, you cannot add more capacity, then maybe you go up to 0.95. So determining what X sub C is what we call V over C ratio, but V over C ratio we want to use, and that will determine cycle length. And once you determine cycle length, the question is how do we divide the green times to the each approach? And we use Webster's method, so-called equal degree of saturation, which I'm going to explain later. But that way we have a so-called critical movements. We get the same V over C ratio. So whether you are in the major road or minor road, most critical movements will get the same performance or services as a V over C ratio. Maybe it may not make sense, but we'll probably talk about it a little bit more. So typically, V over C ratio concept is we provide a big sort of a greenish box, and then actual flows are happening in the shaded hatched area. So that's the V over C ratio volume. And ideally, if you can reduce capacity, then this is going to be longer onto the saturation side, and then you might have a better utilization. Or if you have a bigger capacity, then you can have slightly shorter saturated conditions. Maybe you are often wasting your green time as well, if that makes sense. So the V over C ratio is the key, just fundamental economics theory. And highway capacity is solely based on the V over C ratios. I kind of mentioned this earlier. So X sub C is something we design. This is our sort of usual defined performance of the intersection. I want to define X sub C as something, or in this case, we call it critical value of this is a summation of the critical movements. Maybe I can just give a quick idea of considering these. So you have two phases of these. And then what we want to do is, assuming the same number of lanes and saturation flows, one could be higher volume than the other. So this is a critical, right? And then among these, one is higher. So what we are treating on this V over S ratio is that we don't consider lower volume of V, we only consider higher volume of V over S. So using that and then using another phase, V over S, some of those are key to calculating X sub C. The reason we are doing that is the same as we only control G and C, green time and then cycle length. So when we actually use a critical approach volume and saturation flow rate ratio, and then we have a way to dividing G over C ratio between those two critical ones. Maybe it does not make much sense. Let's go back to that one. So the idea I'm talking about is that, interesting. So the V over S ratio is for the critical movements only. Then if they are different value, so one's V over S ratio is 0.9, the other 0.6. And you can actually give the same V over C ratio by changing C and G ratios, if that makes sense. That way we are creating X sub C to be identical. So we are treating critical movements in the same level of V over C, if that makes sense. If not, probably you can probably exercise this later on, and then you'll see the exact same value is given. So that's how we decided this X sub C. The HCM equation, you probably have seen it, but I'm going to go over fairly quickly on this one. So this one has 3 components. Maybe this is a queuing system, right? I mean, you know about queuing system. You go to Starbucks or toll booth, and the service depends on how many operators and how long they take to serve, and also how many customers and cars are coming in. In theory behind this one is that they are sort of separating uniform arrivals and then random arrivals. So when you want to calculate delay, if everything is coming in as a uniform, it's very easy to calculate, right? You can simply draw the line and so-called triangular polygons, and you can see how many cars are stacking up during the red and how fast they can get discharged during the green, and then you can actually track how many the delay times, and you can estimate average delay per vehicle. That's fairly easy. To calculate for random arrivals, we know it's going to be random arrivals. And in the signal systems, when you have multiple signals and nearby, they don't come as a random, right? So they have some platooning effect, and then they could have arrival type. They could have everyone departed from upstream during saturation flow, arriving green time. That's probably perfect case. And it depends on those situations. So they want to calculate the arrival patterns of those into a calculation of delay. That's a PF, shown as a progression factor. And also D2 is a term for random and then oversaturation delays. It's all based on queuing theory. The challenge of the queuing theory is that when you have a service rate, it's smaller than arrival rate, you cannot solve. It has to be a steady state or equilibrium. But in reality, in transportation, your volume to capacity ratio could be bigger than 1 for whatever reasons, especially when you design the signal in an improper way. So if you have a major street needing longer green and you put the smaller green time, your V over C ratio will be bigger than 1. We have to deal with that situation. So they had to some transpose and then some treatment to consider D2 terms. And then D3 is initial queue. So when you analyze something, there's queuing vehicles there, then you'll have to, they are adding up to the entire calculations. So that's basically described here. So uniform delay is fairly straightforward. X is a V over C ratio. You can actually derive this equation by doing quick polygon analysis. So this is a very straightforward calculation. Again, I mentioned the progression of vehicle to the intersection. It could be upstream, red actually hold the number of vehicles, and they depart as a sort of platooning, grouping, and then coming into the intersection during green. That's a good thing. So this is how to measure quality of progression, and this is sort of approximation. So when you have random arrivals, we put the 1. If you have a really poor progression, this is the 1. Exceptionally good progression, this is what you use. Try to adjust sort of a delay at the intersection level. Even with the uniform arrivals, it's not always uniform. This is a so-called random and then oversaturation or incremental delay. This is sort of derived and then modified based on queuing theory. So this calculates random arrival delay, and K's and I's are for actuated signals and different controller settings and metering conditions. Have some descriptions here, but it's not that important. You can adjust these for actuate the signal, and actuate the signal should work better than pre-timed signals. So that's how they adjusted it. Again, as I said, this is initial Q value. When you have a Q existing at the beginning of analysis, that's just accrue and then add up to the delays, and that's how they considered it. As I said, less than 10 seconds per vehicle is level of service A, and used to be this 80 was 60. Now they are changing it to 80 seconds per vehicle. That's how you define the level of service. So one example, if you want to calculate them, you have a cycle length of 80 seconds and effective green time of 30 seconds, actual flow rate of 400, and then saturation of 1750. You probably want to calculate this as a G/C ratio as 0.375, and then capacity as 656 because G/C ratio is 0.375, and then volume to capacity ratio is 0.609. So in this case, we did not consider peak hour factor. So if you know the peak hour factor, you could have applied it to make it more proper. This is, you are calculating D1 equation. So D1 is assuming uniform arrivals, and if you put this X value and G/C and everything, here one thing I can mention here, this is a minimum of 1 over X. So if X could be bigger than 1, X is a V/C ratio, you just use a 1 because we cannot deal with oversaturated situations, at least for D1 equation. That's how you do it. And then if you have a D2 equations, this is a fairly small. So here, when you have a V/C ratio is small, D1 is major. If you have a bigger V/C ratio, getting close to 0.95 or something, then you have a fairly large D2 term because of fluctuations. And we ignore the D3 term here. So this is the last slide. I kind of mentioned a few times. The impact of downstream congestion is not considered, at least for the HCM equation, and there's no way to consider turn bay overflows because this is analytical equations, and they usually don't work very well. I know I went through very quickly, but I know you actually learned about basics of signals. This is just US version of it, and I wanted to explain some theory behind and also some personal experience and tips for using this technology. So any questions you have or comments?
The turn pocket, like, can you explain how does it?
How does it work, or what do you mean?
How does it happen?
When that happens?
Yeah.
So HCM ignores when they calculate the performance. That's why people use at least the turn pocket. You have to use a simulation model to consider that kind of effect. At least for the link spillover, nowadays the tools are considering those. So when you have a spillback happening at the intersection of the link, and they actually stop the simulation, then this is a bad situation. They try to avoid it. For the turn bay overflow, it's not trivial because this is really happening, and that's affecting a little bit. It's not, so they don't consider that yet. So only way you can do that is a microscopic simulation to deal with it, if that makes sense. So the challenge of a turn pocket is that if you have overflow, and giving longer green is not right answer, because the longer green is always 1 point is a longer red for waiting. So that's challenge. One solution is creating the phase to be left and through together. Let me try the right turn pocket. So this is a road. So you are making right turn pocket and then throughs and this, right? So you could actually have a phase sequence going this and this going together. That way, this is not creating overflow. They can actually, they might have something called demand starvation. There's a lot of throughs and this is not utilized, but still it's better than not having overflows. So if you could not expand your turn bay, and then one solution is using this simultaneous through and right turn, that will solve that problem some level. So phase sequence is a very important parameter as well. Any other questions? Okay, then let's take a 15 minutes and then come back at 11:15. People actually consider dynamic dilemmas as well, which is probably not the right answer. Not here is when the speakers are coming in way past their stereo time, simply extending it. Then everyone will do it, then that's not a solution. What's the type 1, type 2?
Type 1 is basically dependent upon the timings.
Okay, so typical dilemma.
Yeah.
Okay. Type 2
Type
is
2 is dependent upon the driver's behavior.
right.
Like whether he will be likely to go or he will be likely to stop.
Right, that's also associated with the timing as well. So if he's doing it soon enough, then not a problem. I'm not sure the point of type 2. I'm thinking about it educating.
Yeah, more or less it is about the driver's input into that. Because type 1 is like based upon the stopping distance, based upon those things, you can have the timing decided.
I'm not sure. Are you assuming the driver know this will violate? They don't know.
Yeah, they don't know exactly. But the theory we have like type 1 and type 2.
Okay, I understand that. Listen, I don't care whose turn it was. Red just is my color. People don't like red. So providing green whenever needed is the most important for the signal control. This light never turns green. I thought we need to some laugh. Weird signals and happening. Typically, we have a pre-timed, which means timing plans are predetermined. They could change over time of day, but during the same period, their duration never changes. So this was a mechanical way of implementing signal earlier days. And then later, actuated is actually trying to be smarter than pre-timed. The whole idea is provide green where is needed. And then also traffic responsive and adaptive signals. These are well actually deployed in the US, Canada, and even Singapore and other countries. But most of the time we deal with pre-timed and actuated. Same idea of doing it. Again, pre-timed operates on a clock, same cycle splits for the same time period, the designer period, which is not good. Actuated uses sensors, so we need to know how many cars are coming and maybe additional cars are coming. I want to extend my current green time, or I want to terminate my green to give a green to another phase. That's what something that actuator can do. Again, useful to use when the traffic volumes are not steady. It's a varying little bit, not whole a lot. In the US, 70s, they actually started urban traffic control systems, trying to improve control systems. And then adaptive systems like scoots and skets are very popular. This is the UK and Australia developed. Even US actually used a lot of these scoot systems and sket systems. Canada has used a lot of them. And so US actually wanted to have their own. They developed the RT tracks, and in 2000 ACS Lite is, so one of the reasons these adaptive systems are not commonly used was obviously cost of installation is one thing, and also a lot of maintenance. These rely on sensors 100%. If sensor does not work properly, and you get worse situation. So ACS Lite is on an effort to use existing actuated signal and doing better than actuated and close to adaptive control. The lower end of the cost version for adaptive is what ACS Lite. And it actually did a lot of research, but it's not well deployed, unfortunately. It just did a lot of pilot tests and some adapted and then show the benefits. So I'm going to talk about actuated signal a little bit. The basic concept is when you have a pre-timed, your so-called capacity, which is based on duration of green time and cycle length, is fixed over multiple cycles. And in reality, vehicle arrivals are often same as the capacity or higher or lower. So the demand is higher than capacity, queue will form, so vehicle will wait longer. And if a vehicle arrives lower than capacity, you are wasting your green time. So the idea is that can we adjust these in a somewhat dynamic way, try to utilize it better. So the simple idea is that knowing this, can I shorten my green time to have a lower capacity? Can I increase my green time a few seconds more to take care of additional demand? That's actuated signal. So traffic demand actually controls the timing. That's good. Actuated is indicating greens are changing based on arrival patterns. But it's not a solution for all congestion problem because it has a limitation. It only works with up to the maximum green. It's another term, but so you have a pre-timed signal having duration of green time, and the actuated is not really creating adaptive way of changes. It does have a max green time, and it's only changing green time between minimum green to maximum green. If every approach is congested, everyone uses the max green, it's not working. It has to be in between. And obviously, it can reduce delay, and it handles very well on short-term fluctuations and better utilizes the capacity. Disadvantage is obviously cost. So pre-timed, you do not need sensors. You just set the dial and then continuously showing in sequence of the fixed durations. And a lot more complicated settings that you have to do it, and also maintaining detectors are very costly, and then you do not really well known in advance that detectors are not working. You probably know when there are calls coming in and there's a problem. That's another challenge. Actuator has a semi-actuated fully and volume density. Semi-actuated is where you have a minor street, does not carry a lot of volumes, but the volumes are on the major just so high, unless you have a traffic light, they could not make right turns. They could not even make a left turn easily because of heavy flows. So you want to open the signal and give it right away on the minor street once in a while. And this could be maybe a school in and outs. It's heavy vehicle flows, and we only need it during the school hours, and then they actually can operate those, things like that. Fully actuated is every approach is actuated. Volume density is needed for high-speed approach because I'll explain later, but the way the actuated signal works is that it's extending green time whenever new arrival is coming within fixed duration of time. We call it extension time or gap time. So basically, cars are coming in less than 2.2 seconds. We continuously provide green as if a lot more cars are coming in. And when you have high speed, even though low volume, vehicles are coming so fast, they can still continuously extending greens, which is not good. So to avoid that, we use a volume density. I'll explain later. So I'm going to explain this one, and then a lot of the slides I'm going to skip. So this is a way to understand how actuated work. So this is a minimum initial, and this could be fixed the minimum green. But actuated signal has sensors, right? So it could count how many cars are coming during red. So you count the 4 cars. You want to at least give 8 seconds so that 4 cars can get through. So minimum initial could be dynamic. So based on count of the sensors. And this is a situation that cars are coming in. This is arrival patterns. So this is there are different controllers doing different things. So one thing we want to do is that if there's no cars waiting, you don't have to consider terminating my green time. So often this is called the demand call is made. So I'm giving green for current approach or both directions. And if those approach with the red, if they actually have a car waiting, and I start doing countdown, if that makes sense. So countdown is happening that this is at the end of the minimum initial, and I have a countdown of say 2.2 seconds. So I'm counting down these. This is a time gap. And if the new arrival comes, I reset. Okay, there's a demand coming in. I'm going to continuously give green time. And I'm counting down, reset, 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 reset. And I'm counting down, this is the duration of whatever, 2.2 seconds or whatever you define. No cars are coming. Then I'm going to say, oh, okay, I served enough demand. But this is maybe a very small number of cars are coming. It's not worthy. It's better to serve those approach with the waiting cars. So I'm just going to yellow, and then red clearance time, and then next phase of green starts. So this is a more efficient, in a sense, compared to fixed durations. Hope that makes sense. So the phase, I'm going to skip this. Oops. So minimum green, phase time, patch time, these are the same thing. Max green is needed. So we don't want to have green time going forever. There's waiting cars. Somehow there's a lot of cars are coming in. If you give green time for here too long, and there's a violations. So you want a max green that turns over to next phase, even though cars are continuously coming. Recall is something that when you have a detector not working, you want to have a max recall. Max recall is creating your green to be maximum green. So it's a sort of trick. And you usually have a minimum recall, which means that when you have a major street and even though no cars are waiting, you actually give a minimum recall. That means that you want to start green to minimum, and it's giving fake demand call to minor streets. Again, the reason is major street usually have more cars are coming soon. Even though there's no cars waiting, I'm going to give that minimum recall. That way, minor streets just start the countdown immediately. If it's too complicated, don't worry about it. This is usually they comes with the default, which is no recall. But volume density is another feature I mentioned. So the volume density, as I mentioned, the reason we want to do this is that when you have a 45 miles per hour or higher speed, cars can come quickly in terms of time, even though number of cars are not many. Compared to 35 miles per hour, they can come 2.2 seconds a lot quicker than lower speed. And that is creating continuously extending green time, even though you don't have many cars that are coming. So the idea behind here is that you have same duration of extended green gap out time or extension time, but you give a time to reduce. So this means that, hey, I'm going to give only 10 seconds or 15 seconds of this extension. After 15 seconds, this is getting to be smaller and smaller, so that gap out can happen quickly, can terminate quickly. That's useful because high speed, usually they can continuously extend the green time. So that's what volume density is. The nice picture to determine what parameters are needed. Okay, so actuated is very useful. Obviously, Synchro and 27F should be able to model actuated signal as well, and they do. Synchro is a software that can model, simulate, and also optimize timing plans. And it is considered as a macroscopic and deterministic model. It sounds like not good, but they have a really smart way of designing timing plan. So you can actually evaluate timing plan. Means that you can simulate conditions and estimate the delay. It does consider actuated signal, which is good. And this is a sort of a new terminology, percentile delay. As I said, the highway capacity manual is doing average only. And now the HCM is considering reliability factor, which is considering fluctuation of the demand and other things. Percentile delay is actually considering that, recognizing that optimizing for only average flow is not going to work very well. They define 5 percentiles. So instead of using average as 100%, they're using 10th, 30th, 50th, 70th, and 90th percentile volumes, and each is worth of 20%. So they consider 100%, but it's considering different percentile of the flow. So if you get 400 average, you get maybe 20% near 400. You get probably 2 standard deviation higher for another 20%, or 2 standard deviation lower for another 20%. So they are simulating these conditions, so their timing plan can be okay for even 90th percentile case. So this is a way of considering reliability, which is very good. And when they optimize, cycle length is sort of a sequence of evaluations. I want to have a cycle length of 40, 50, 60, 70, 90, 80, 90, 100, 120. They do these one by one and find whatever the best cycle. And then green splits, this is interesting. They are doing heuristic approach. I mentioned about equal degree of saturation, which is giving critical movements of getting same volume to capacity ratio by adjusting duration of green time. They don't do this, and it works good. They actually favor major street, which carries more vehicles, and then often that helps reducing delays as well. And then phasor sequence is you can try all combinations, so it's almost exhaustive search. And offsets, they don't do every second of offset value. They do quasi-exhaustive search. If you know the optimization, it's more like a bisectional optimization, if I may give you one idea of doing this. So this is a maybe 0 to 1 range. You have this x value, and you evaluate this, that, and that, and this is showing that this kind of trend. So optimization should be in this area. You ignore this part. That makes sense? So if you evaluate 3 points, and then you can lose one portion, half of the portion. You continuously do this, and it may not be true if this is something like this, but this is good enough for them, so that's how they do. They cannot do every second too much. So percentile delay is optimized, and then a lot of people complain about it's not doing the HCM method, so they added the HCM method as well. You can get many different measures, emissions and number of vehicles in the dilemma zones and other things. So I want to explain percentile delay a little bit. I kind of briefly mentioned Poisson distribution is assumption. So we talked about this. Poisson has a property as average equal to the variance. So once you know average, you know the standard deviation, you can quickly calculate the percentiles. And based on that, you can calculate percentile of 10th, 30th, 50th, 70th, and 90th vehicle per cycle. So you can actually get the arrival rate based on the V as a flow rate, a number of cars per hour, C as a cycle length, and you get the average flow per cycle. And based on that, you use the standard deviation of the average, which is your standard deviation. So this is one example of calculating it. These are the assuming normal distribution as z-score values. So 0 is a 50. If you use 1.28, you go 90th percentile. I don't know you know this. So this is sort of giving 1.28, and that's only 10%. So you find the 90th percentile value. 0.52 is giving 70th, and minus 1.28 is going this way. So you are on that range. So this will generate the average volume per percentile area. So using that equation, you can use, say, 120 vehicles per hour for 60 seconds. Average would be about 2 vehicles per cycle. And if you're looking at the 90th percentile, it's giving about 3.8 vehicles per cycle. So it's about almost twice more cars coming. So this is where synchro would work a lot better than HCM method. HCM designs timing plan for average flow, which is 2. And synchro considers, I'm going to deal with 90th percentile, which is happening, not all the time. You can actually handle those situations. Maximum Q is it's a one limitation of the HCM method. In the HCM method, when they calculate uniform delay, let me see. So in the HCM method, this is what happens. This is what they do. Oops. I'm not good at this. Okay. What I meant is that in the HCM method, they actually have, this is the number of vehicle arrival during red, and vehicle is continuously increasing. At the beginning of green, cars are just moving together. But in reality, they don't. They continuously have a queue length increase and then reduces. So HCM is a delay only this portion of it. So it's not realistic. It could be huge difference. It could be small difference. But theoretically, it's not correct one. So they actually fixed this problem by tracking backup queue. So delay is based on percentile, weighted average of different percentiles. It's fairly straightforward. They also consider random plus oversaturation, just like HCM method. They use a similar equation to calculate that. And then the way they optimize this is individual intersection timing, and then at the individual they do splits and cycles, and they also do a partitioning of network. So when you have 100 intersections, and then optimizing for entire 100 is very time consuming and also not needed, especially when you have a large spacing between the intersections. Sometimes you have maybe more than a kilometer. The rule of thumb is that about 3,000 feet, that's more like 1 kilometer, I guess. When vehicles are departing together as a group from upstream, and they travel about 3,000 feet away, they almost become random arrival. They usually don't maintain that grouping of platooning. So if you have intersections are far away, and you don't really have to consider coordination, that takes time. And then synchro is using coordination factor. They use about 40 seconds of travel time. So it's longer than 40-second travel time. It's not really necessary to consider coordination and things like that. So they do have a partitioning of those, and you can also go back and then optimize for entire network, because you want to go with major intersection cycle length. It's critical intersection cycle length. So some minor intersection which might have a smaller cycle, they can actually use a slightly longer cycle. It's probably okay. And then doing offsets and then phase orders. So the optimization is done. This is probably something not easy to get from the manual. It took some time to figure out this. So based on manual, they are saying that they optimize green time to serve 90th lane group flow. It means that if there's a possibility, I'm going to provide green time for 90th percentile. Make sense? You can do this only when the demand is not very high. Demand is high, you cannot provide the 90th percentile for everywhere, unless your cycle is huge, which is not good. And if 90th is not available, then they try to do the 70th or 50th. So they'll try to provide higher end of the demand if possible. And then when they decided these into the each phase, and there might be remaining time, but the cycle length is fixed, and then needed 90th is a different value, they put into the main street. So they favor main street. By doing this, they are not treating each critical movement as the same. Their volume to capacity ratio of critical movements are not the same. Compared to the HCM method, the principle is that they want to have an equal degree of saturations. So this is a very interesting way of doing it, and it works. So this is one example. You have the same example of a previous one. 120 seconds of vehicle cycle length. 50th was a 2 vehicle. 90th was a 3.8 vehicles. So you would give either 4 seconds for HCM. Now this is almost double. 8 seconds for the synchro. Second phase has a heavier demand. So if you had a 50 percentile, 17 seconds, 70 vehicles are there, so you would give about 34 seconds of green. 90th is 24, so you have 44 seconds of green time. So given the 6 seconds of cycle length, you would divide these. So if we are doing for 90th percentile, right? So this is your duration of green time. So you divide them into those. There's no remaining green time. So 44, 52. So this is no remaining green time. But so each phase has 4 seconds of lost time, we assume, 8 seconds total, and we give 8 seconds and 4 seconds. And if you calculate the VOC ratio, they are not identical. If you had used the HCM, they would have given green time so that these two values are same. And this violates a fundamental engineering principle. Webster's method is violated, but it works. And so equal degree of is not done. When VOC ratio is bigger than 1, synchro try to balance the VOC ratios. At low volumes, extra time is sometimes given to measure, or sometimes evenly divided. How do you optimize cycle length? They try to determine cycle length, shortest cycle length that clears the critical percentile traffic to accommodate the fluctuations. So shorter cycle, if they can do 90th percentile, it's better. So shorter cycle usually works better, even though people think that shorter cycle is going to be less capacity, but it's not. They do have this principle of doing that. And longer cycle is only needed when there is a close to the congestion. If your ratio is close to 1 or bigger than 1, they try to only accommodate 50th percentile volume. So again, this VOC ratio is bigger than 1 is happening when you have a 90th percentile of the cases. Then this easily goes up to 1, over the 1. And the over capacity situations, they actually have some way of finding so-called performance index instead of using delay. So they kind of wait on the stops as 10 times higher than delay per second. Stop is causing a lot of problem for progressions and others. So they kind of wait into this. And this can be changed as well if you want to. And the offsets, they do bigger steps at the beginning. So instead of doing every second, they do 8 seconds. So you have a lot smaller number of evaluations. And once you find the optimal 8 seconds, then you can do 4 seconds and then 1 second. That's how they do. How do they consider actuated signal? So this is another sort of computer science approach. They cannot optimize extension times or minimum greens or detector settings like minimum recalls or max recalls or no recalls. They only evaluate. So if you want to sort of optimize actuated setting, you can play these values in synchro. But at least they consider this as simulating actuated. So in the actuated signal, one good thing is possible phase skip. If there's no right turn vehicles waiting, then you don't have to serve right turn by providing 5 or 6 seconds of green time. They can do phase skip, it immediately goes to through. So through can have a longer green time for providing better service. Or gapping out. So gapping is that I'm going to give a green time for this phase. After minimum green time, if not many cars are coming in, I'm going to stop the green and go to next phase. So this will be modeled. So they are looking at the phase will be skipped if a probability of a zero vehicle arrival is greater than 50%. So this is a percentile that we calculate how many vehicles per cycle, and they flip the coin and then change that. And if expected number of arrival vehicle is less than 0.69, they assume zero vehicle arrival, so they make a phase skip. And then time to gap out is based on Q clearance chance, and then they can do gap out. So this is a sort of embedded into the simulation, and they can model it. That's a good compared to the HCM method. As I mentioned, in the HCM, they use a K value to just adjust the delay. They don't even consider a realistic way. Coordination, I mentioned. Coordination keys, I guess, they consider coordination factor. As I said, if an intersection is about 40 seconds or longer travel time distance away, coordination is not needed. One thing they don't do is that they don't consider platooning dispersion. I'm going to explain that in 27F if I have time. So what it means is that when number of queued vehicles departing as a saturation flow, they are not moving as a train. They actually get dispersed a little bit. And then how much that is dispersed is obviously many factors. How fast the first vehicles are going and other things. So there's a model that 27F is doing, and they don't do at all. They just move this is going to as a train. They could have done it, but they probably wanted to save computation time. So one criticism is that maybe except for isolated intersection, Poisson may not be valid. they assume the uniform arrival for actuated signal. That's easy to calculate. And then there's no carryover of delay for the vehicles remaining at the end of each cycle. So this is only considering that those 10th, 30th, 50th, 70th, and 90th are happening as independently. They don't happen as a sequence. They just totally independent. They just use weighted average. But it's a very commonly used and very nice graphical interface. And it does have actually microscopic simulation, so-called the sim traffic. So whenever you have a synchronous network, and you can actually run micro simulation with the one click away. They figured out all the inputs you have in synchro. They can actually run a microscopic simulation. That's good. It has an interface with other tools. So that's a synchro, and I'm going to talk about 27F for just another 10 minutes. So this was a UK tool that Robertson is a probably well-known person in the UK back in 1967. And then US adopted this tool in 1981 to improve signal optimization tool. And it does have a simulation. They assume uniform arrival as well. And then, again, Platon dispersion is probably a very big deal for 27F. They do consider cars are dispersing over distance and travel time. And it's been considered in the optimization. That's a very good. And again, delay, uniform delay is assumed, and then they are adding this random plus oversaturation delay, same as the HCM, same as the synchro. And they deal with the oversaturated conditions by tracking the end of queue, and then when the link is oversaturated, and they know this is oversaturated conditions. They optimize everything. They used to have a hill climbing method, and they recently adopted a genetic algorithm as well. So they have many objective functions. You can actually have any combination of these measures. So they are using, again, performance index, similar to synchro during congested conditions. It's a linear combination of delay stops and maximum queue penalties and even excess of the operating cost. And then they also consider progression opportunity. If cars are moving into continuously going to next intersections, they create a bandwidth type maximization, which is a progression opportunity. And when they have oversaturated conditions, they try to maximize the throughput, which is not a bad option, but it sacrifices minor street people. So the idea is that when you have oversaturated, you want to provide green times to approach with a higher volume. That's how you get the maximum throughput. Pros and cons. They have a macro way, but they do some step size and also do inflow, go flow, and outflow. So obviously inflow is arrival, go is a saturation, outflow is whatever inflow coming in, and outflow is a departure flows. This is probably the most important component of 27F. Given the time, maybe we go quickly. So this is an idea, maybe this is easier to understand. The idea here is that every single vehicle is possibly in the fraction of vehicles. In reality, it's not. But they do this, so it's easy to generate that way. So here, this is the saturation flow rate. Oops, I'm going to just clear out. This is probably a few vehicles, right? So they depart at the beginning, and then they'll probably arrive downstream at the t time later. But they assume people go faster than speed limit travel time. So they multiply 0.8. So that'll give cars can arrive a little bit earlier. People do while speeding. So this one vehicle could be creating this kind of profile. Next vehicle is creating another profile, and creating these number of vehicles are creating this sort of arrivals. So this arrival may not be one vehicle arrival at the downstream, but this is used for optimizing timing plan for downstream. It's more realistic. than random arrivals. Remember, HCM is assuming uniform arrivals. They don't consider these. They only consider arrival types. But this is a more realistic way to macro level, but almost the micro level simulation of arrival patterns. And this has been very, very useful for optimizing timing plans, at least for transit 7F. And also, you need to worry about computation time. So this equation is calculating, once you have a Qt flow, initial flows departing, and Q prime is a predicted flow rate at the downstream at the happening. So this is once you have a Qt, and this is just easily calculated without having any complex computations, just all linear computations. All you need is that smoothing factor of F value. Smoothing factor is basically, if you have out of nowhere, there will be wider dispersion. If there's a lot of downtown and parking maneuvers and delivery truck activities, this will be smaller. So the alpha, so-called the Platon dispersion factor, is the empirical value, but usually 0.35 to 0.2, 0.4 range. And this will give you reasonable approximation of the dispersion. So that's very easy to calculate and then worked very well. So this is how you actually calculate this F value. This is based on the travel times of the vehicles. And it's empirically driven again. If there's no interactions on the roadway side, then you have a lot quicker travel time. Some reason of parkings and others, you have a longer travel time, kind of reflected in this curve. Again, the friction factor values usually use a 0.35, and it could be lower and higher. More frictions are having a lot more parkings and pedestrians and other things. So one example of calculation is that maybe we have a distance about 1,000 feet, speed of 44 feet per second, beta of 0.8. Beta is again, it's not using post speed limit. People go faster than actual travel time. So we are reducing by about 20%. And we can update every 2 seconds. And we assume alpha is a 0.35. And you can calculate these values here. So this is basically, big T is based on 44, 22.75 seconds is needed. If we assume some people are speeding 80% of the time, and it will arrive about 18.18 seconds. And then this T2 prime is based on 2s. 18 seconds is equivalent to 9 intervals of every 2 second updates. And then this will give where the vehicle would be. And then assuming these alpha values and T's, F is going to be 0.24, which is how we divide the vehicles into spreading out. And this is what you're going to be seeing, that first the vehicle is arriving into these ratios, and then if you add them up all, this is what you get. So 4 vehicles are departing over 10 to 18 time steps. And then first step is 0.24 vehicles, 4.2 vehicles, and so forth. So this add up into 4 vehicles, obviously, but they will have this spreading effect. And if you have actually, this is only throughs, right? So right turns and left turns, they can actually add them up together. And they are all sort of contributing into the arrival pattern at the downstream. And this will create how much of the offset should be adjusted, and also the duration of green times for these platooning, they can be calculated. So that's a very important feature. This is actual calculations. You can easily do in Excel. So the equation itself is a very fast calculation. Alpha has some impact, but it's not huge. And obviously some critics is that if you're only evaluating for 2 cycles or 3 cycles, you lose some vehicles. If you're doing 1 hour simulation, it's fine. But most of the optimization is done for 2 cycles, and then they try to optimize. And lane changings and then some of the vehicle interactions are obviously ignored. They hope to capture them by alpha value, if you can actually do it. Last piece I'm going to talk about is optimization method. So I'm going to show you this with just graphs here. So again, this is a heuristic optimization. what I assumed here is that this function, this is actually true function which we do not know. This is how much delays or performance measures are changing over different offset values. And we don't have a closed form equation. So we don't have this equation in reality. We only know by evaluating a different offset value. So they have an offset value of sort of step size. So they call it, this is step size 1. So they go, first offset they evaluate, this is their objective function. So this is their objective function value, right? So this is the value I'm get, and I go another step, this is what I got. So if I want to minimize it, right? This is the first value, the second value. Oh, that means if I go continuously going this way, I may get better performance, the lower value. So they go another one. They got here. Okay, this is not good. I don't want to go continuously. I can probably go back. That's smart, right? And then they have another step size equals 3, S2. Now I want to go backwards. See, this was not good. I'm going to backward. It's giving huge delay. I don't want to go that way either. So I still coming back here. And then I have a step size 3. I want to go that step size. Oh, this was a smaller. And I can do another one. This is not good. I come back here. And then I have another step size S4. I did it. It's not good. So I find this as sort of optimal. If that makes sense. So this is a heuristic. Depends on the step sizes. But it works pretty well. It's a lot better than evaluating every second of the cycle, which you have to do 100 seconds, you have to do 99 times or 100 times. And this will give only 7 times, getting very good results. I mean, the true optimal is here, and you are very close. I mean, this is an example. No guarantee that you will find the optimal solutions, but that's what people usually do. So it has been used a lot, but it's obviously giving suboptimal solutions many times. They adopted a genetic algorithm, which we're going to talk about in the afternoon. I think this is it. Different step sizes can be used as well. This is I basically explained. I mentioned about oversaturated situations. They track back of a queue. So this is basically what it is. They at the beginning of a green, they continuously track back of a queue by looking at a portion of cards are leaving, continuous arrival cards are just stacking up back of queues. So if that back of queue is exceeding linker capacity, they can recognize there's a spillover problem. They actually added that into the model. That's it actually. This is a quick overview of traffic signal optimization timing tools, and they can actually consider buses and other multi-modes as well. It's just a matter of combining them, and you also can give weights for buses if you want to optimize for. I'm not sure about rickshaws and other things, but at least those can be done. Any questions or comments? Okay. In the afternoon, we'll probably use a computer program. It's just Excel is all you needed. And we'll try to actually do optimization of timing plan using traffic volume and genetic algorithm, and see if you can appreciate the way of using optimization.
We have emailed you the Excel file, so please check it and just download it on the laptop.
Thank you, guys.